There's special software for that.
You can do it on Windows now without software too.
Oh, is that so?
Yeah.
Ah, okay.
So QuickTime is there on Windows?
Windows 10 has a
Windows
video
10.
recording stuff.
That's a criterion. You have to upgrade first. All right. So this presentation is basically going to focus on image processing, but it's going to be in a really high level. So in case if you're not in image processing, you'd still understand what's going on, because image processing is pretty intuitive and visual. So it's not very difficult to follow what's going on. All right. So as we introduced ourselves before, we wrote a book. It's called Image Processing and Acquisition Using Python. It's published by CRC Press. The book basically, as the name indicates, it talks about both image processing and acquisition, because the processing that you do, it actually depends on what image you have. You can't just apply any algorithm to any image. You have to apply algorithm that's specific to a specific modality. Okay, so that's why we have both the topics in the book. Anyway, so the content of this talk is we'll start with image processing pipeline. When I say image processing pipeline, most of the image processing work I've done will actually fall under that pipeline. Okay, and that's a very good way for people who have never done image processing to understand how image processing actually works. Okay, I can keep image processing very mystical, but the reality is it's not that mystical. It's actually fun, and I want you to enjoy and have fun with it. Then we'll talk about the very basic image processing operations like filter, segmentation, morphology, and measurements. Okay, and then again we don't have that much time, so I'll focus only on like one filter and one segmentation, and then I'll gloss over these two, but I'll provide you the presentation and the program, so that in case if you want to play around with it, you can play around with that as well. Okay. So this I gave as like a 2-hour talk, so it's just a lot longer. So, all right. So, so what is an image? Generally speaking, we're all familiar. If you've never done image processing, at least you're familiar with photographs, for example. That's an image. Okay. It basically is a two-dimensional representation of a three-dimensional world, and each pixel or the subunit of an image will encode some information. Okay. So in case if you're taking a picture of a flower, then it's basically taking a representation of a flower and it's in the image. Okay. So that's basically what image is all about. In the case of CT, MR, and things like that, the meaning gets a little different, because now you no longer are talking about just something that's in the physical world, but you're also talking about some deep physical phenomenon that has happened, which gives you those pixel values. Okay, so that's the difference between a photograph versus more of a medical images. Okay. An important concept to understand is pixel size, which is actually a fundamental unit of an image. So the smallest chunk that you can break down an image, you can think of that as a pixel. Okay, and that pixel actually has a physical dimension, because when you take a picture of a flower, the flower, let's say, has 2 centimeters in diameter, and your picture is 100 by 100. That means 2 centimeter is of pixel width 100. Okay, so which means you can go from pixel to the actual physical unit centimeters. Okay, so that conversion is the pixel size. Okay, and that's how we actually can go from the pixel world to the real world, because you can do all the calculation in the pixel world, but eventually you have to give output to people who understand it only in the physical world. Okay, 100 pixels don't have any meaning. 2 centimeters, yeah, definitely has meaning for everybody. There are many formats in Python. If you use like SciPy or SciPy or scikits, you can actually read most of the photograph type images. Those are like JPEGs, BMPs, PNG, and things like that. Okay. And then there are specialized Python modules that can read medical images and microscope images. So, image processing pipeline. I want to make it really simple by going really high level. So you start by reading an image. Some people say you also create an image, but most of the time you actually read image. Like 99% of the time you read images. So you read an image, and then you have to do a series of processing, depending on what you need to do. Okay. So let's say your task is to take a picture of a flower and then separate the flower from the background. Okay. When you take a picture of a flower, there might be something that is undesirable. Okay, there might be noise or might be some bad pixels. Okay, You get rid of them before you can do your segmentation. In that case, you do this operation called filtering. Okay, so filter is basically an operation that allows you to remove unwanted stuff. You can think of it like that. Okay, but it's more than that. But it's a good starting point for him, for people who are learning image processing. So segmentation is the process where you separate that flower from the background. Okay, so you have the flower and you are giving one, you identify all the pixels that belong to the flower as, let's say, pixel value of 1, and all the pixels that are not in the flower as belonging to a 0, for example. Okay, so this process of separating the flower from the background is called segmentation. Okay. The process of segmentation is basically dependent on what images you have. Okay, for example, if you have an image with a lot of occlusions, a lot of stuff in the background, then your segmentation gets more complicated. But if it's really smooth background where you have like a blue background in the back and then there's a red flower in the front, you take a picture, it's just really easy to segment. Okay, so the degree of segmentation basically depends on how you are going to separate, or what are the stuff that you don't want to be part of your object, and that basically brings the complexity. Okay. And then there are other processes like registration. In painting is a very complicated operation. At least it's intuitively simple, but mathematically it's a complex operation. Imagine, okay, you don't even have to imagine. Most people know when all these glamorous photo shoots and all that, they do this airbrushing. Okay, that person might have a wrinkle and then they just and then it's gone. Okay, so that process you can actually automate it using this thing called in painting. Okay, so you can add brush stuff, you can remove bad pixels and replace it with something that is much better, using this process called in painting. Okay. The book doesn't talk about it, but it's actually a very interesting mathematical operation. And then there is morphology. Morphology is actually a really cool concept. I'll talk about it when I come there. Okay. In fact, most people, when I was working in Minnesota, most students will come to me and say, students or faculty will come and tell me, here's an image, I want to do some work. Okay. And most of the time, these work turns out to be really simple. It'll be a combination of a filter, a segmentation, a morphology, and some measurement. Okay. And then they'll have to wait for me to do it, and I might have a big backlog, and I don't have the time right now. Whereas they could just do it themselves in probably like 20 lines of Python. That's all it will take to do the same work. Okay. And once you do all these things, you might want to either write an image or you visualize an image. Okay. That's basically the image processing pipeline in a very 10,000 feet level. And that is most common and the most occurring workflow that you will find in image processing. Okay. There might be some nuances here and there, but it's essentially these are the work that you do. Filters. So I have a URL here. This URL basically is for scikit image. Scikit image. So NumPy is a numerical Python. SciPy is scientific Python. And then there is the scikit image. So what they do is whenever they want to add stuff to SciPy, SciPy is really big. It's complicated. So what they do is they first experiment by putting it into a module called scikit. And scikit has many sub-modules like scikit image, scikit learn, and all that. So they first put it into scikit, make sure it's working fine, make sure it's being used a lot, and at some point in time, it might move to SciPy. But most of the time, I've seen things haven't moved that fast. But they still stay in scikits, and they're not experimental. They are usable. Okay, but it just turns out that that's the workflow they follow, where they go from scikit and then they move to SciPy. Okay, so I use this a lot, and the scikit image basically gives you lots of filters that most people commonly use. Okay. Ooh, I don't know what happened to this font here. I don't know, suddenly it disappeared. Alright, sorry. 1 minute. I need to show you the formula. There you go. doesn't let me choose. Okay. Right. So I'm going to take a very simple operation. It's called contrast stretching. Okay, the idea is actually beautifully simple, but it's also very useful when it comes to images with really poor contrast. Actually, I don't need this. Okay. All right, so here's an image. It's very hard to see the contrast. This is actually an electron microscope image. Contrast is pretty poor here. And then I'm going to stretch the contrast so that I get an image that looks like this. Okay, this image is unusable. You can't see it. Even with the computer, it's impossible to process. Whereas the very simple operation like this, I can get an image like this, which now can be processed. Okay. The reason we have a problem is this image is called a histogram. Okay, so along the x-axis is pixel value and along the y-axis is frequency, which means at any point, let's say this is pixel value of 100. That means the 100 is happening so many number of times. A pixel value of 150 is happening so many number of times, etc. Okay. Now, sometimes the histogram turns out to be something like this. It's pretty narrow, even though the original image has a much bigger, wider range of pixel values possible. Okay. What this contrast stretching is basically doing is it's taking this, pushing it to the left, taking this and pushing it to the right. Okay, so that your histogram is more distributed. Okay, so that's basically what it's doing. And to do that, it actually does a very simple operation where it takes the original pixel value minus the minimum in this image. The original pixel value, every pixels, minus the minimum pixel value here, divided by the maximum pixel value minus the minimum pixel value. Okay, and then multiplied by 256 or 65535 depending on what bit depth you have. And this process alone, this simple operation actually gives you something like this. Okay, and if you want to look at the code, the code for doing this, there is a bunch of code for reading images. But so these are the modules that I'm importing. Then I'm reading the image and preparing it so that it's a NumPy array. Okay. Similarly, here I'm doing the writing. So this is the portion of the code where I get the maximum value of the image and I store it in B, minimum value and I store it in A. And then I convert the image into float because normally the images are always integers. I convert it into float and then I do this calculation and I convert back from an image, from a NumPy array to an image so that I can save it. Okay, pretty intuitive to read. It's you don't have to loop or anything. This operation, when I say C minus A, C is an array, a NumPy array, and A is one number. Okay, I didn't loop through every pixel value in C. I just said C minus A, and it subtracts one number from the whole array. Okay? Similarly, when I say divide by B minus A, which is also one number, it just divides every pixel by that number. Okay, so it's as simple as that. It's very intuitive to read as well, because if you look at the formula and you look at this, it looks exactly the same. There is no difference. This is the original pixel value minus the minimum divided by max minus min times 256. In case 255, I had to put it because it starts with 0. Python starts with 0. Okay, so that's a cool thing about Python. It's like it literally reads like your pseudocode. Your Python scientific programming code will look like a pseudocode. All right, another example is histogram equalization. So here's an image, which is an X-ray image of a chest of some patient with some lead in it. The contrast is pretty poor because you can't see the nodules in the lung. We're going to use a different operation called histogram equalization, and then now you have an image which is much better contrast. Okay, and to do that, you actually don't even have to write the code. You don't have to write much code. If you really look at it, so this portion is literally the pseudocode for. If you look at a histogram equalization pseudocode, it'll look pretty much like this. It'll say, go and get the cumulative, or first get the histogram, then get the cumulative sum for that histogram, and then calculate this value. This is the formula for histogram equalization. And then you do this division, and then convert it back into an unsigned integer 8, because when you store, you always use an integer. And then I'm reshaping it. Okay. So this pseudocode, this is exactly like a pseudocode, but written using Python, and is fully functional. Okay.
In the library, histogram library, somebody wrote that library, right?
Yes, it is there. It's part of NumPy. So I say np.histogram. So NumPy has the histogram method, which you just say, here's an image, and here is the, I think this is the number of bins and the range of pixel values, and it'll give you the histogram. Okay. So I know I'm not going into depth because this is very hard for everybody to understand all the details behind it, but all right. So the way histogram equalization works, it works kind of like contrast stretching, except it does a little more differently, which is histogram is like this. The final histogram also looks kind of like stretched, but it does one more thing. When I do contrast stretching, literally all that I'm doing is I'm moving this there and moving this here, and this becomes flat, right? Because there are only so many pixels. This has to become shorter. Whereas in the case of histogram equalization, it not only stretches it, but makes the histogram as horizontal as possible. Okay? An ideal histogram should have all pixel values of equal frequency. Okay? But there is no such ideal image, because you are taking a picture of something, and there is nothing like ideal. It's a real world. Real world is never ideal. But ideally, for image processing purpose, it needs to be as flat as possible. Okay? So the histogram equalization allows you to do that. Okay? All right. So that's two filter method I'm talking about, but scikits actually has many more. Okay? And if you want to program other ones, you can literally take pseudocode for most of these filters. Just follow the pseudocode and you'll get a Python code from there. I wrote for my work, I wrote a prototype filter called triangle segmentation, and I basically followed the pseudocode for triangle segmentation. I just did it, okay, and it looks just like the pseudocode, maybe a few more lines, but because Python has its own rules, you have to follow those rules, but otherwise it's basically the pseudocode. Segmentation. I already told you a little bit about it, which is the process of separating an object from its background. Okay, that's one way of thinking about it. But you can also separate, if you have multiple objects and you want to separate each of those objects out, you could also use segmentation for that. So, in this example, so let's start with this, and then I'll talk about. So this is a work that we both did. It's published as a paper. So we were given this mice data, okay, very high resolution mice data, microCT, and we were supposed to segment just the bone alone at very high resolution, okay, or very high fidelity. The image is already at very high resolution, but we want to get it at high fidelity. So we use this process called Rene entropy. So you have this, you see this gray thing here? That's a slice. Okay, that's the microCT slice. And all these white things that you see, those are the bones in the microCT. Okay, so we were supposed to separate from all these background noise, like all these gray pixels. You're supposed to separate this white at high fidelity. That was basically the work. And we use this algorithm called Rene entropy, which is not part of scikits, but scikits actually has other segmentation, which you can go and check it out here. But we programmed Rene entropy, and the way it works is, if you have a histogram of an image, you calculate this guy called Rene entropy, H alpha. Okay. You calculate the total Rene entropy to the left of it or to the right of it, and then the sum of those two is called the total Rene entropy. Okay. And then you keep repeating this process for every pixel, and the point at which this Rene entropy is at its maximum is the threshold. Okay. So which means, if let's say this t is the threshold, then all pixels below are considered as background, all pixels above are considered as foreground. Okay. In our case, everything above T was our bone, and everything below T was background. Okay. Sorry, a tissue. In real case, it's actually tissue, but we didn't care about tissue, so we just forget it. Sorry. All right. So we took that segmented bone, and then we had something else as well. We had to superimpose PET on top of it and things like that. But we had to superimpose the BMD, bone mineral density, on top of it and things like that. But anyway, so with the segmented bone, we are able to visualize just the bone alone. Okay, and all those tissues are no longer visible here. Okay, and the code. I'll share the code with you. Don't worry about all the details behind it. So I have this function called Rene seg underscore function. Okay, where I give an image and I give the parameter alpha. Okay, you remember there is a h alpha in my equation. So the parameter alpha is nothing but 3 here, and then this function returns a threshold, the t that I was talking about. And then I just have to threshold the image by just saying thresholded image equal to I am greater than thresh. Okay, simple. You don't have to loop through anything. You just say this array greater than something, it gives you a thresholded image. Okay, it's all in NumPy magics. And the Rene entropy is also not complicated. So I build a histogram, and then I do some probability distribution functions and things like that, and accumulative sum of probability distribution function. And then for every pixel, you remember I was telling you, for every pixel value in the histogram, you have to calculate total entropy to the left and the right, and then you sum the two. Okay, so that's what I'm calculating here. H1 and H2 are the left and the right sum. And then eventually, once I calculate for every position in the histogram, I sum it by doing T equal to H1 plus H2. Okay, so this is an array of numbers, 255 of them. H2 is another array of numbers, 255 of them. Add the two, it just adds one element 1 in one with element 1 in the other. Okay, it keeps repeating that process. Okay? Again, no loops, nothing. Literally reads like a pseudocode. All right.
What is your input? What is the image?
The image, I don't have an image right here, but I can show you when I run this video. Okay, maybe. So do you see this white area? That's the bone. Okay. So there is a slice that's running through this. Okay, there's a CT slice that's running through this, in which all these bones, all these white spots that you see, they're all bones. Okay, and then there is tissue, because the bone doesn't stand by itself. There's tissue surrounding it. So these are all tissue, the mice tissue. Okay, we had to remove all these tissue and keep only the bone.
So the image is actually three-dimensional.
Yeah, it's a three-dimensional, correct. Yeah.
Yeah,
Thank
okay.
you.
A CT scan.
Yeah,
CT scan,
And so
yeah.
the gray area is all just one part of that. It's one 2D image from the 3D image.
Yeah, think of it like a slice taken like this.
Okay.
I'll have tissue, bone, and everything. Similarly, we took a slice across a mice, and you will see tissue and bone and everything else. Okay.
Is that one image or?
Oh, there is actually, this one has 6,300 images.
Oh, okay. So, okay.
It's really big. 20 is basically 2K by 2K by 6,300. It's a huge image. It's probably one of the biggest one I've worked. 50 gigabyte in size. Oh. Morphology. This is actually one of my favorite. Okay. The idea is, when you segment, let's say you have two objects and you segment it. Okay. You say you come up with some rule that anything more than this pixel value, I'm going to assume is foreground. Anything lower than this is background. Okay. Now, let's say there are two circles. You figured out these are two circles that belong to the foreground, and everything else is background. But let's imagine a scenario where these two circles are supposed to be independent circles, but for some unfortunate reason of the way the image has been taken, poor quality and all that, the two circles are touching each other. But you want to separate them out. Okay? How would you do it? Morphology. Okay? Morphology basically defines two simple rules. The first operation is called dilation, The second operation is called erosion. Okay, as the name indicates, dilation means grow. Okay, so when in the dilation operation, you're basically making each of those objects, those two circles, grow in size. Okay, you can grow by 1 pixel, 10 pixel, 20 pixel. You choose whatever number you want. Okay. Similarly, erosion is the opposite of dilation, where you shrink. If the object is of size 100 pixel diameter, you can shrink it to 99 pixel or 98 or 95, whatever the number you want. Okay. These two operations alone actually are pretty powerful when you think about it. You can combine them. You can combine them with other operations, and now you have like a magical way of cleaning up objects, things that you don't want to be seen in your image after you do the segmentation. Okay. The combination operation, one of them is opening. Opening is you erode and then you dilate. Okay. And closing, you dilate and then you erode. So you use these two operations are not exact opposite of each other, because when you erode something and then you dilate, okay, it's not same as dilating and then eroding, because we are talking about discrete pixels. We're not talking about a continuous system. Okay, so there's no guarantee that if you do this and then you repeat this, you'll get the original object back. There's no guarantee. In fact, there's pretty much no guarantee when it comes to images. Most of the time, it'll just 99% will not work. Okay, but what will work is you can use these two operations and the combination of these two operations to actually clean up your image. Imagine you have a scenario where you have these 2-3 circles, and then you have a lot of tiny dotted circles lying all over the place. You don't want those tiny dotted circles. You want to get rid of them. So how would you do it? You can just do a closing operation. You do open operation where you basically erode. Okay, let's say you erode by 5 pixels. Then all those circles that are like 5 pixels in diameter, they're all gone. Okay, and then you dilate back, you get your original big circles, but all those small circles are all magically gone. Okay, all by using a very simple operation. And you don't even have to program. Scikit provides all the tools for it. You just call opening or closing, or dilation or erosion. It has more operations as well, like top hat, bottom hat, and all that. But anyway, so these are the things.
Could you give us an example of when you would actually dilate and then erode?
You will dilate and then erode. All kinds of crazy sounds. Sorry. So dilate and erode. So there is one scenario where you will have two circles touching each other, pretty close to each other, but you want to separate them out. Okay. Then if you erode, then they will separate. Actually, they will separate. Let me think about it. Sorry, I don't have a quick example on top of my head, but I'll think about it and tell you. So morphology. So that's the morphological operation. It's a very interesting idea. You should check it out. There's a guy who actually did his PhD on it, and then he became famous just for this. Actually, he then went on to expand the same concept across many domains, and he's been pretty successful in that. The last topic is measurements, at least as far as this talk is concerned. Python actually, the Scikit provides a lot of tools for doing measurements on images. So you have an image and you have like a bunch of stuff and you want to study their statistical properties. Is this thing circular? Is this square? Is this rectangle? Okay, you can study all that using measuring, skimage measure. Okay. So here's an example. So you have an original image where let's say your aim is to find the bounding box for each of those objects. Okay, and you also want to find the centroid. Okay. A good example would be let's say you have a series of videos where you want to track people. Then you could use something like this to separate. You can separate the foreground from the background by using some segmentation. And then you put a bounding box around each person and just follow the bounding box over time. Okay. So you have the original image. Then we segmented this image. This is easy to segment, as you can see. There's discrete objects. But even for complicated objects, you can do segmentation. And then you label each of these. You say, this one has a label of 0, 1, 2, 3, 4, for example. Okay, and we are giving different colors to indicate different labels. And then once you label them, then you can put a bounding box using the measure tool that I'm talking about. You can actually put a bounding box around each one of them, and then you can also get all the centroids corresponding to each of these regions. A good example that we have used it in is something like cell counting. You have 300 cells. The way some faculty will do is they will take a high resolution photo of it and sit there and count. Okay. Whereas if you do it like this, it takes like probably 1 second. It just goes like that and calculates everything. It calculates not only how many are there, but it can actually tell you this particular cell is of this diameter, or this is the bounding box size, and things like that. Okay, all by just using like 1 or 2 seconds of calculation, okay? And probably like 20 minutes of coding. So
If you know how to do Python.
if you know how to do it, but you will learn it. Don't worry. Yeah. So to show you an example of that code. So this term called region props is actually borrowed from MATLAB, because MATLAB has a function called region props, region properties. So the Python guys, the NumPy, SciPy guy, Scikit guy, they basically borrowed the same name so that people who use MATLAB can easily transition to this. And the way the code works is pretty simple. You basically take the original image. You take the original image here. You read the image. Yeah, you read the image, and then there is a method called Otsu thresholding. It's just one of the segmentation methods that comes with scikits. You use this to find the threshold. I threshold the image. Now I have these 5 objects all nicely separated. Then to label, I just have to call label. Okay, I didn't have to actually do any calculation. I just call label, and it just labels each region. And then to get the region properties, I just call region props. And now I have all the statistics of all those 5 regions stored in this. I think this is a dictionary, D. It holds all these properties. Okay? And then the rest of the stuff I'm doing is all just plotting. As you can see, I'm just plotting the bounding box, the centroid, and things like that. So the code looks big, but really speaking, there's only 3 lines that actually have significance. Threshold it, label it, region props. That's it. Okay. So that's a quick introduction to some aspects of image processing. But I just want to quickly conclude by, we discussed it before. Before my presentation, we were talking about the various Python distributions. He pointed out Anaconda. There's another one called Nthought Canopy. There's another one called Nthought Canopy. They have a free and paid version. I think the paid version is like $200. In either one, I think the paid version is like $200. Not much. And then there's Python XY, which is completely free. There's no paid version for that. Okay, so you can check out these 3. I highly recommend these 2. One of these 2. Python XY is not bad, but I have had some students who actually had problem using this. When they were using it, it didn't work as we expected it to be.
The one installed on the Mac already.
That's pure Python.
Yeah,
Okay.
That's not a distribution.
yeah, that's just built from the Python distribution by Apple.
Yes.
And bundled with the OSX image. So
Yeah,
Yeah.
that's right.
These include things like NumPy or SciPy or some of the other tools that he was using.
Mm.
Yeah, those tools are sometimes not simple to install. Like for example, NumPy uses Boost library, or SciPy uses Boost libraries, and then compiling all that stuff is not for everybody.
Mm.
So that's why these distributions are actually making money. That's so complicated that they can make money from them.
Small libraries, right? More
This
specific
comes
libraries.
this comes with all the libraries, like maybe 100 or 150 of modules that are pretty popular for scientific community. So you just open it and you use it, and it's there. And they have their own ways of updating these modules and things like that. So you actually literally don't even have to go to the command line if you don't want to. And then these are some other image processing libraries that I use. NumPy, SciPy, Scikits. Scikit-learn for machine learning. This is pretty good. Really good, actually. Then there's Mahotas, which is a very small library, does some incredible stuff fast. But it doesn't have the variety of functionality that Scikit actually provides. And then there's Matplotlib for plotting. We actually used it in the example. And then there's OpenCV. This is a really, really good tool, OpenCV. It has C++ and Python backend, frontend, or whatever they call it. but I'm using it with Python. So that's that. Any questions?